Hello everyone, it's Samir here, and today we are going to look at a problem which seems very easy conceptually as well as easy to comprehend. But if you follow the normal path, you are going to get involved in messy calculations. Okay, so we'll see the problem. It states that if 2 points P and Q on the standard hyperbola are such that CP is perpendicular to CQ, where C is the center, you find 1 upon CP square plus 1 upon CQ square. Okay. So I would recommend to you that you first try and solve this problem on your own. Okay. Give it one attempt, two attempt. Okay. And you see, the kind of messy calculations you get involved in. Okay. And I selected this problem so that you learn that we can have, a better approach and to choose which kind of path we should take in a particular problem, okay, for a shorter solution. Okay, so for this problem, we obviously first get a basic diagram. Okay, we make a standard hyperbola with center at C, mark points P and Q so that CP and CQ are perpendicular. Okay, now we have to prove that 1 upon this distance square and 1 upon this CQ square. Okay, we have to find this out. Okay. Now, the traditional approach that mostly would be deployed solving this problem is either you assume the point P and Q to be x1, y1, x2, y2. Okay. And try to find the inverse of square of distances, substituting x1, y1, x2, y2 in the hyperbola. Or another approach is better one is that you take P as a sec theta, b tan theta, and Q as some a sec alpha or b sec alpha, and then try to solve it. In both these approaches, you are going to lead to pretty messy calculations. Okay. So a better approach here is, especially in all those problems where distance from center is being calculated, is to try polar coordinates. Okay. Now, for those of you who are not aware of polar coordinates, the basic is the x-coordinate of any point. Okay, if its distance from origin is r and it is making, say, angle theta, okay, so its x-coordinate would be r cos theta, something like this, and y-coordinate would be r sin theta. Okay. Okay, so r represents the distance from the origin and theta represents the angle the line joining that point and origin makes with positive x-axis. Okay, so here for this problem, we assumed P to be R1 cos theta, comma R1 sin theta. So length CP will be R1 and angle it makes with the positive x-axis will be theta. Okay, so if for P we choose R1 theta as its polar coordinates, since Q is like at 90 degree from CP, okay, so its angle would be theta plus 90, okay. And obviously, its distance from origin would be different. So Q becomes R2, some other distance, into cos of theta plus 90 and sine of theta plus 90, okay, because we are getting Q by rotating P by 90 degree and changing its magnitude, okay, or distance from origin. So Q comes out to be, we cos 90 plus theta is minus sine theta. So Q comes out to be minus R2 sine theta, comma R2 cos theta. Okay. So now we have got both P and Q in terms of R1, R2 and theta. Now the only thing that we need to do is we need to put these points in the hyperbola given. Okay. And see what happens. So when you put P on hyperbola, because it should satisfy the hyperbola, okay, so instead of x, we put r1 square cos square theta upon a square minus r1 square sin square theta upon b square equal to 1. Okay, so we take r1 square common from the left hand side and take it to the right side. So we get 1 upon r1 square, which is same as 1 upon cp square. Okay, as cos square theta by A minus sin square theta by B. Okay. Similarly, Q, we put minus R2 sin theta and R2 cos theta for X and Y, and we get R2 square sin square theta upon A square minus r2 square cos square theta upon b square equal to 1. And again we take r2 square common, okay, shift it to the other side. So we get 1 upon r2 square equal to sin square theta upon a square minus cos square theta upon b square. Okay, how 1 upon cp square plus 1 upon cq square is always constant independent of the position of p and q. Okay, so we allotted some random points to p and q, and you can see as the coordinates of p and q are changing, 1 upon cp square plus 1 upon cq square remains constant. Now coming back to our problem, we had already found 1 upon cp square and 1 upon cq square. So we just need to add them to get our final answer. Okay, so adding them, we get 1 by cp square plus 1 by cq square. Okay, so if you will add them, okay, you have common denominator a square. So you will get something like, okay, cos square theta plus sin square theta upon a square. Okay, and these two terms are in negative, so it will be minus sin square theta, okay, plus cos square theta, since both are negative, and we have taken minus as common, upon b square. So this would become 1 and this would also become 1. Okay, so 1 upon cp square upon 1 upon cq square here comes out to be 1 by a square minus 1 by b square. Okay, so we are able to get the required value with, just very simple substitution of the polar coordinates in the hyperbola and just adding two equations. Okay, so the importance of this problem is to know when to take polar coordinates, when to use Cartesian coordinates, and in which kind of problem, which one is going to save you more time and benefit you more. Okay, so for more such insights, new problems, and unique solutions, keep watching further videos and see you in the next problem.